Okay, lesson 1.2, finding limits graphically and numerically. You will be able to estimate limits numerically and graphically and show when a limit fails to exist. On this first slide, my prompt is, what do you know about this thing already? Sketch a graph and fill out the tables using your grapher's table feature. So if you take a look at this function, we see x cubed minus 1 all over x minus 1. And the idea here is to generate some thoughts about what do you know about this rational function already in terms of vertical asymptotes, possibly a hole, end behavior, x-intercepts, things of that nature. So I will give you a second to come up with some ideas about what this thing looks like graphically, or what do you know about this function already. Okay, so some of the things you may know about this function is that we have a cubic function divided by a linear function, which could possibly make this look quadratic looking or parabola looking, which it does. Another thing you may have noted is that the end behavior for this graph, as we plug in positive or negative infinity, the top is outgrowing the denominator, the bottom, so that means that as x goes to positive infinity, the function goes to positive infinity. Likewise, if x goes to negative infinity, the top is going to result in a negative divided by the bottom is also negative, so again, going to positive infinity. So you possibly know about the end behavior, but the goal of this lesson is to take a look at where we have domain restrictions, and possibly you found out that when x equals 1, we have a problem. From this table, we could assume that the limit as x approaches 3 should be negative 60. If we look at the values really close on both sides, we can see that we're 4 thousandths off from 60 in both directions on that. On the next table, again, I'm just going to draw the x-axis, and I am interested in as x approaches 3. Okay. And again here, as I look from this direction, we have got negatives getting bigger in the negative direction, so it appears that at 3, for the values less than 3, it's probably doing something like that. And on the other side of 3, so these values right here, think about writing it in from the right side, these are getting bigger to positive, really big numbers. So we could think that as x equals 3, we have a vertical asymptote possibly on this graph, and the point is, from each direction, these are pointing to two different things. So in this case, we can say the limit does not exist. Now the last one. This one is actually one of the more confusing of our examples. It tends to be misunderstood by students. So as x approaches 3, I can see, looks like I've got pretty close to a linear function decreasing a little bit. Okay. And what is confusing about this is, trying to make a dot there. Okay, there we go. That's the best I can do for x equals 3. What's confusing about this is, as we come in from this side and as we come in from that side, I ask you, what does it seem like should be here? And what confuses students is they say, well, it seems like, I don't know, because there is something there. Whereas we look at the last examples, we always had some kind of problem, undefined. The limit doesn't care if there's a problem or not. We can do limits of undefined values, but the prompt is still the same. What does it seem like should be there? Well, if we look, it seems like the value 5 should be there. And our limit is 5. And the function value is 5. So this is one that's confusing to students because they run into real conceptual issues when the function's defined there. The limit doesn't care if it's defined or not. It just says what seems like it should be there, whether it's there or not. Now on this slide we have two rational functions, and this one's just a straight up rational function, a quadratic on top, a linear on the bottom. This one over here is a rational function, but we also have a square root symbol going on in that denominator. So I want you to take a moment and just think about where are the x values that we run into problems with, or in other words, where are their domain restrictions. Take a moment, think about that. And after you've given that some thought, go ahead and put these in your grapher. In the y equals screen, you can look at a graph if you'd like. A table is sometimes more compelling evidence of what a limit should be. But in both, we are given two different limits. In this one, we're interested as x approaches 2. In this one, we're interested as x approaches 0. So take a moment to do that in your graphers. Okay, in this left example, hopefully we saw with our grapher that the limit approaches 1, or is 1, I should say. It's approaching 1 from both sides as you look at the table or look at the graph. And the right example, we get that the limit is 2 as x approaches 0. Now down below, I have an alternate question. How do you write this function's domain in interval notation? So this is kind of an interesting one where not only is it a rational function where we have a 0 in the denominator, but we also have this component where we don't want to have a negative in our radical. Okay, that's beyond the course of this calculus class. So the x values that make the radical negative would be anything less than -1. -1 is okay to put in there because we get a 0, and 0 minus 1 is a -1 in the denominator, and that's okay. And we'll get a 0 on the top. But anything less than -1 will make this radical symbol go into the imaginaries. Okay, so we have that. Also, we know that when x equals, so let me write this down, x has to be greater than or equal to -1 because of that piece right there, the radical. Also, if x equals 0, then we run into another problem because we'll get the square root of 1, which is 1, and then in the denominator, 1 minus 1 will give us a 0 in that denominator, and we run into other problems. So we actually say x cannot equal 0 either, but anything above 0 is fine. And again, we're not concerned with a 0 in the numerator necessarily at this point. We can have a 0 in the numerator because 0 divided by some number is 0. It's a 0 in the denominator. That's our issue. So to answer our question, how do you write this function's domain in interval notation, we're just going to recap this. Domain could be written as, okay, so our lowest value can include -1. So we do a square bracket, comma, we can go all the way up to 0 before we run into our next problem. Can't include 0, so we do a parentheses. So we're going to do that with a union of the set. So we're going to jump over 0, not including 0, and then after 0, greater than 0, we can go all the way up to positive infinity. And any infinity always gets a parentheses. We never can include a positive or a negative infinity. It's not a number we can get to, it's a concept. So we're doing this prompt because you have some homework questions, and a lot of your answers for domains and ranges are in interval notation like that. On this next example, I give students a while to do this with their teammates, so I encourage you to pause the video here and see if you can put together a graph and a table of this function. Hopefully you were able to come up with the table. So piecewise functions is something you'll have to be pretty familiar with, pretty good at for this class. Piecewise function says here for these x values it's that thing, for these x values it's that thing. So this one's kind of interesting because it says basically f of x is equal to 0 when x equals 2, and that's the only x value that it's equal to 0. Otherwise it's equal to 1 everywhere else, x not equal to 2. So what that's going to look like is this. So we scale this. It's going to look like the linear function or the constant function y equals 1 everywhere except, whoop, right there. We run into a problem, or maybe not a problem, but something else. So it's going to look like that horizontal function y equals 1 everywhere except for this part right here. When x is equal to 2, whoops, having problems with this. Okay, dot. Trying my hard. Okay, so I'm just going to make an X mark because I'm having trouble writing a dot on this program. So there should be a dot right there. We'll make it a mega huge dot. There we go. Okay, so this is what this graph looks like. The table is over there. Graph is right there. Now, our question asks, find the limit of f of x as x approaches 2. So let's write that down. The limit as x approaches 2 of f of x is equal to, so again, change colors here. As we come in from both directions on the table, what does it seem like should be there? Or you can think about it graphically. As we ride this graph in from that direction and that direction, what does it seem like should be right there? And again, even though the function value is defined at 0, what seems like it should be there looks like 1. And so that is the limit. Even though the function value is defined at a different place, it seems like it should be 1. So the limit is 1. Okay, on this slide, this is one where I let the students work together at their tables and come up with all of these. So I'll give you, I will have you pause the video here, see if you can do these on your own, and then I'll just have the answers in a moment. Now, if you notice, these are kind of grouped up, as in these first two have to deal with the x value 2. So question number 1, what is f of negative 2? Well, when f of x, or when x is negative 2, we can see our function is defined at an output of y equals 3. Okay. Number 2 says, what does it seem like should be there as we approach negative 2? So again, this is the idea of limits. What does it seem like should be there? Well, both sides of this graph are pointing to the output of negative 4. Okay, so the function value up here is 3, but it seems like when x is negative 2, it should be 4. Sorry, negative 4. Okay. Questions 3 and 4 are regarding the x value of x equals 1 right here. So again, number 3 is saying, what is f of 1? If you look there, it's got 2 open circles for both sides of the function. So we would say that this is undefined, or you could say does not exist. That's usually a term we use for limits specifically. Undefined is something you hopefully are familiar with. And question number 4 says, what does it seem like should be there as we approach x equals 1? So from this side, it looks like it's pointing at a y value of 2. As we approach x equals 1 from that side, it looks like 0. So again, because one side is 2 and the other side is 0, this limit does not exist. 2 different values. Switch colors here. 5 and 6 have to do with the x value of 4. So question number 5 says, what is the function value at x equals 4? It looks like the y output is 4, and the limit, again, let me erase this circle here now. What does it seem like should be there as we come in from both directions? So on the left hand side it looks like 4, but on the right hand side it seems to be about 6. So again, because they're not the exact same value, limit does not exist. Even though the function is defined there, limit does not exist. And switch colors one more time. 7 and 8 have to do with the x value of 0. Let me clean this off a bit. X value of 0. So what's happening as we go into that x value right there? So f of 0, we can see that the function value, having trouble with the dots on this program, looks to be about, we'll say, about 3.5. It's about my best guess. I can't do a decimal either. There we go. And again, the limit says what does it seem like should be there. As we come in from the left and as we come in from the right, it looks like it's also pointing at 3.5. So in this last case, the function value and the limit were actually the same thing because it pointed to and was defined at that same place, that same y value. Now on this last slide, here, these are some interesting limits, more like interesting functions that you possibly aren't familiar with. If I asked you just to think of what the graphs of these look like, you could possibly put them together on your own with just some mental computation or some, cranking out some tables, but these are fairly unfamiliar functions at this point. So what I would encourage you to do at this point is, that one you should be able to do if you just do kind of a sign analysis. This one you could think about for a bit, but this guy right here is a little strange, and what I want you to do is see if you can come up with the graphs mentally on your own, and then double check by putting them in your grapher and ultimately answering the question of each of these limits as x approaches 0. Okay, so on this first one, the limit as x approaches 0 of absolute value of x divided by x. This graph, think about it this way, is on the right-hand side when x is positive values, you're going to have a positive over a positive, which results in, and your numbers are dividing out to give you the number 1. But when x is negative, the numerator is going to always be positive, the denominator is going to be negative, so we get that. And then what is happening at 0? Well, 0, if you plug in 0 for x, you get 0 divided by 0. So it's a domain restriction. So we're going to have open circles on that graph. And sorry, that's the best I can do with this stylus utensil. So the idea is, what is the limit as we come in from both directions? You could look at your tables as well, but the limit does not exist. Whoa, okay. So, and again, it's because -1 and +1 are infinite amount of numbers apart. On the next one, this graph, as we approach 0, this has a vertical asymptote, and from both sides, this is increasing without bound to positive infinity. So this is kind of a special case where I like the answer, the limit is infinity. However, our book has a convention, or a definition I should say, that a limit has to be a real number. So it doesn't let us get away with infinity for the answer. It says the limit does not exist, which I'm going to accept both those as correct answers. If you are offered a multiple choice test, this, in my opinion, is the better answer because it is more descriptive of what it's going to on both sides. It's going to positive infinity from both the left and the right hand sides as we approach 0. So I like that answer better. The last one. This is an interesting function. I'm not going to scale this by coincidence, or by convenience is what I meant to say there. So here we have, this is really hard to see on a grapher. Online graphing like Desmos does a lot better, but we have kind of the oscillation of the sine function. And what happens is, as we get closer and closer to 0, this thing goes back and forth harder and harder, and then eventually returns on the other side. If you were to zoom that graph in, Desmos does a really good job of this. You can see that, and it just starts getting hard, oscillating back and forth harder and harder. And again, a TI grapher is just going to go berserk here and not really do a very good job of this. And it's going to start looking like just basically all shaded in, and then kind of calms down the other side. And if you zoom in far enough, again, keeping that kind of range scale the same, this is just going to be nothing but a blockaded bunch of squiggles going up and down. So it's kind of cool to see on Desmos, because as you zoom into the origin, it just gets denser and denser. What's happening with this function is the closer you're getting to x equals 0, the harder and harder this thing is oscillating. So this is an interesting limit. The limit does not exist, and if you think about our definition, what does it seem like should be there? If you're looking at the tables as you zoom in and zoom in, it just keeps picking random values between positive and negative ones as outputs. It's not tending to anything. It's not getting closer to 0.5 or 0 or anything like that. It's just oscillating faster and faster as you get closer to 0. So this is a kind of a, I don't know, I guess in my opinion, a rare case of a limit that does not exist because of oscillation. We know there's a problem when we plug in x equals 0 because we have 1 divided by 0 in that function. But if you think about what the graph's actually doing, it is oscillating harder and harder. So anyway, limit does not exist on that example.